I just want to briefly mention that ordinary generating functions are not the only way to represent a sequence with a simple function. And actually there's an important one that plays a very important role in analytic combinatorics that I just want to mention briefly now. You can define other types of kernels to represent the sequence. So instead of z to the k, say we put z to the k over k factorial. If we do that, then what we have is what's called an exponential generating function. So for example, the sequence of all ones, the exponential generating function that represents that sequence is z to the n over n factorial. And we saw that's e to the z. And the powers of 2, again, just do the math. 2 to the n z to the n over n factorial, that's 2 to z to the n over n factorial, that's e to the 2z. So same sequence, different functions for representing them. And there's situations where it's more natural, it's better, it's more convenient to use exponential generating functions. And many other possibilities have been studied. But for analytic combinatorics, we're going to focus on ordinary generating functions and exponential generating functions. So it's worth spending, here's another one, n factorial itself. The exponential generating function for n factorial is 1 over 1 minus z. So that's an example of when we might need it. If you've got a sequence that grows very fast, like n factorial, ordinary generating function is not going to work. Sum of n factorial z to the n doesn't converge for any z, and it's cumbersome to work with. So use exponential generating function, that's 1 over 1 minus z. That can be a bit confusing because the same functions arise in different contexts, but really not. It's just a different way to represent the sequence. And we have the same kinds of operations, and you can read in the book about differentiating, integrating, and so forth. And there's one important operation that's what happens when you multiply two EGFs. Then you get what's called a binomial convolution. And that's just applying the same steps that we used when we were proving what happens with the product of two ordinary generating functions, but we carry through the k factorial in the n factorial. So distribute, now when we change n to n minus k, we've got a k factorial n minus k factorial. But then we need an n factorial in the denominator anyway, so we multiply and divide by n factorial, and now we've got a exponential, after we switch orders, we get an exponential generating function for this convolved sequence, the binomial convolution. And actually there's plenty of applications where these kinds of sequences arise, and we'll see them very soon. So there's recurrences, say, related to such problems that arise, and if confronted with a recurrence like that, we'll have to know naturally from the problem that one looks like I should use an exponential generating function on. So this is an example that actually we'll come up with some similar examples in specific applications related to important algorithms later on. So Fn equals sum on k of n choose k, Fk over 2 to the k. How we're going to find an equation for that number? Exponential generating functions, we'll use the same rule, except we make an exponential generating function. So that is multiplied by z to the n over n factorial and sum on n. Then on the left-hand side, we get f of z, and on the right-hand side, we get a double sum. And then what we're going to wind up doing is kind of working backwards for the convolution that we just did. So switch order summation on that. That's just switching the sums and keeping, now if it's all k, then n's got to be bigger than k. And then change n to n plus k. So that brings us n plus k in the top of the binomial coefficient, and the exponent is z, and n plus k factorial. And then do some, as the n plus k factorials cancel out, We still have the fk, the z to the k and the 2 to the k absorbed together, and the z to the n. And now those are independent sums. So that's the binomial convolution backwards. And so what it says is that f of z equals e to the z. That's z to the n over n factorial sum. And the other one is f of z over 2. So f of z equals e to the z f of z over 2. And that's something we can telescope. And this is a little bit formal. It's not necessarily true that it converges, but let's not worry about that just now and work with the idea that we've shown that f of z equals e of 2 to the z, e to the 2z. And what's that? What's e to the 2z, the exponential generating function for? That was one of the first examples that we looked at. It just says that fn equals 2 to the n. In this case, whether or not the generating function converges, we've got an answer that we can check. 2 to the n definitely equals sum on k, n choose k, 2 to the k over 2 to the k. That's the binomial theorem. So looks like a difficult recurrence actually has an easy solution with exponential generating functions. And and it works for similar functions too, and that's what happens in the practical applications. Maybe it's n minus 1k, or maybe there's an extra term of some kind. The same process works to actually tell us the facts that we need to know about the algorithms that we're studying. We'll see in much more context the important role that exponential generating functions take when we look into analytic combinatorics in a couple of lectures. But even in the context of just solving recurrences, they can be important, as this example illustrates.